Now let's talk about convolution neural network, also known as CNN.
So let's begin with the problems of traditional neural net. Suppose we have a neural net. This is input layer, we have a hidden layer, and we have a output layer. Okay, these are same neural net. And this is input image. Actually, this is image letter A. So each pixel is connected to input node of layer, input layer like this. Okay, so for example, if you select these 4 pixels here, so each pixel is connected to input node of network like this. Okay, so in this particular input image, we have 2 white and 2 black. Okay. Okay, now let's say we move this original image to the left by 2 pixels. You shift just a little bit by 2 pixels, okay? And then what happened is, for the same reason here you selected here, in this original image, you have 2 white, 2 black. And right now, if you after you shift the image just a little bit, now every pixel is now black. Okay. So actually, what happened is, so if you move this big image to the left by 2 pixels, what's going to happen is there are actually 154 input change in this image. Okay. Actually, 77 of them changed from black to white, and 77 of them changed from white to black. So that is drastic change, okay, in terms of the pixel values. But clearly, they are letter A, same letter. Another example is like this. So in the original image A, let's say you give some damage like this, or like this, whatever. You can do many things. You can sometimes you rotate the letter, or you squeeze the letter, or you can squeeze even further. You can do a lot of things, okay? And for each of these images, their pixel values are very much different to each other. So if you use traditional neural net, because the input values pixel values are very much different, traditional neural net consider these are different letters. That is the problem of traditional neural net. But actually, as you can see here, every image here is basically A. Okay, nothing changed. So that is the main problem of traditional neural net. So in this chapter, we're going to solve this problem by using a number of techniques. And that neural net, a special neural net, is called CNN, and that's what we're going to study in this chapter.
So in previous slide, we have seen the problem of traditional neural net. So CNN network tried to solve those problems using kind of 3 weapons here. So it has 3 techniques to solve the problem. The first one is, as I mentioned here, the first one is weight sharing, and the second one is called sparse connectivity, and the third one is called pooling layer. Okay, we're going to explain this one by one from next slide and on. So by using these techniques, CNN solved those problems in previous slide. And another problem of traditional neural net is, in traditional neural net, every neuron in the network is connected to every neuron in the next layer. Okay, so for example, you have a certain node in hidden layer. That node is connected to every node in the lower level hidden layer. Okay, that's how it is connected in traditional neural net, and it is called fully connected connection, fully connected, right? So because these neurons are fully connected, the problem is if you add more hidden layers, then the number of parameters actually increases exponentially. Okay, so let's say you add a few hidden layer there, then the number of parameters, basically the number of weights, actually increases exponentially. Okay, actually, it's out of hand. Okay, and it definitely causes overfitting problem. So that's another problem of traditional neural net. So in CNN, we need some method to reduce this number of parameters in the network. Okay, so again, to reduce the number of parameters, CNN uses the following techniques I mentioned earlier: weight sharing, sparse connectivity, and pooling layer. Let's talk about this one by one. So if you compare CNN with the traditional neural net, the main difference lies in the difference in hidden layers. So in hidden layers, actually there are two different kinds of hidden layers. The first one is convolution layer, and the second layer is pooling layer. So in CNN, we have two different kind of hidden layer. So here in this slide, we're gonna discuss convolution layer first, and then pooling layer will be discussed a little later on. So let's take a look at the convolution layer in CNN. So in convolution layer of CNN, actually it consists of multiple what is called feature map. So in one convolution layer, there are many feature maps, okay? And if you look at one particular feature map like this, okay? And also, let's say we have input image, or if the CNN has multiple convolution layer, this may be the feature map of a previous layer, okay? But for now, let's say this is input image, okay? So we have one feature map, and let's say this is an input image, and let's take a look at how these are interconnected. So if you take a look at one particular node in this feature map, this is actually connected to a small portion of input image like this, okay? In traditional neural net, okay, each node in hidden layer is connected to every node in input image or every node in previous hidden layer, okay? It's called fully connected. That's the way we connect node. It's the way the nodes are connected in traditional neural net. But in CNN, it's different. CNN has, in the convolutional layer, has multiple feature map, okay, and in one particular node in feature map, actually this is connected to a small portion of input data, okay, not the entire input, okay. And also similarly, in a similar way, the next node, or this one is also connected to a smaller portion of image like this, okay. And in a similar way, let's say this node is connected to a small portion of image like this, okay? So each node in feature map is connected to a small portion of input image. That's the first difference, okay? So let's say this node is connected to these 9 node in previous input image, okay? And also, let's say for this node, this is connected to this 9, okay, node in input image, okay. And each link here is associated with a weight value, right? Each connection has its own weight values, right? So suppose we have these 9 weight values for these 9 links, right? We have 9 link here between this and these images, this input node. We have 9 link here. So for each link, we have weight values. So these are the weight values for each link here. Okay. In a similar way, for each, let's say for this node, it also has this 9 connection, 9 link, right? And it should have its own weight values like this. So what is interesting here is in a convolution layer, these weight values must be same. Okay. So the weight values for this node, the weight values for this node, whatever it is, let's say this is the weight values for this node, okay, is exactly same as, let's say, the weight values for this node. Okay, these are same. And in a similar way, for the weight values for this node, and this node is again connected to 9 node here in this input image, right? So the weight values for this node is also same as the weight values for this and this. Okay, so for every node in a feature map, their corresponding weight values are identical, same. Okay, that's the second difference in convolution layer feature map. So these are two main difference in convolution layer, okay, of CNN. The first one is in a node in feature map, it is connected to only a small portion of input. Okay, that's the first difference. Second difference is for each node, its corresponding weight values. Okay, these are identical. Okay, for each node, their weight values are same. And these are the differences in convolution layer. By the way, these weight values, okay, between feature map node and the input nodes, these are called convolution filter or kernel. Okay, but basically what it means is these are weight values between this feature map node and the input images. Okay. Convolution layer has multiple feature map. Okay, so let's say we have another feature map. Okay, feature map M, okay. And this one also, again, this one also take a read input from input image. Okay, they use the same input image like this. And so again, similar way, this feature node here, feature map M, take a look at this small portion of input image. Okay. Again, so this node again take a look at this part of input image, etc. Okay. So within the same map, within the same map, each node shares the same weight values. Okay, within the same feature map, but in different feature map. Okay. So the weight value, this one, is same across all different nodes in a single feature map, but their weight values are different in different feature maps. So in the same feature map, their weight values are same, okay, but in different feature map, okay, their weight values may be different. Within the same map, their weight values are same, but these values and these values are different. Okay, so that's the way how we construct the feature map and convolution layer. By the way you compute this value of node in feature map, let's say this is for how we compute this. This is very easy. This is just the inner product between this input and the weight values. It's very simple. 1 times 1 plus 1 times 0. Just inner product. Okay, it's element-wise multiplication. So that's why how we get 4 here. Okay. So these weight values are sometimes called convolution filter or kernel. Okay. And every node in the same feature map, okay, every node in the same feature map actually shares the same weight values. Okay, it's called weight sharing. Okay, and every node in feature map look at small portion of input. So if each node in the feature map looks at the
small portion, not the entire image. Okay, that's called the sparse connectivity. Okay, and each node in a feature map looks at different region of input. So it is like this. We have a feature map, and it's like this. This node, okay, this node actually take care of this area only. Okay, so it's this guy say, oh, I don't care about the rest. I care about this area only. Okay, and in a similar way, this guy say, I'm interested in this area only. I don't care about the rest. Okay, so it works just like that. Okay. And these weight values, these are not given by human. You don't decide the values of weight. This is determined. Okay, this is determined by algorithm automatically. It's by training. Okay, so that's a convolution layer.
This picture shows some examples of convolution layer. So as I said, a convolution layer in CNN actually consists of many feature maps, okay? And as I said, each node in a feature map actually looks at a small area of data, okay? And each node in one particular feature map, actually for these nodes, their weight values are same, right? But in different feature map, okay, within the same feature map, their weights are same, but in different feature map, their weights are different, okay? So that's structure of a convolution layer. This one actually explains how to compute the value of feature map. So this is the input image value, and let's say this is the kernel convolution filter, basically weight. And the output of feature map here is actually the element is inner product, element-wise inner product, element-wise product. Okay, so this one is multiplied by this one is multiplied by this one, etc. Okay, so add all together, it becomes 4. Okay, that's how you compute the feature map values. So the way we have many feature maps in convolution layer. So the way we look at the feature map is the following. In CNN, you can assume one feature map is about finding a certain pattern in the data. For example, we have a convolution layer, you have many feature map. We can assume like this feature map is about finding horizontal line, and we have another feature map, and this feature map is about finding vertical line, or this feature map is about finding edges, or this feature map is about finding, let's say, circle, etc. Okay, so you can assume the goal of feature map is like this. This feature map has a kind of a goal of detecting something in the original data. Okay, so that's the goal of feature map. Okay, so that's why each node in feature map shares same weight. For example, this feature map, let's say if this feature map, goal of this feature map is to find, let's say, horizontal line. Okay, so then this node actually, this node in this feature map is trying to find horizontal line in this area of image. Okay, that's what's happening here. And in a similar way, the node in this node in this feature map, same feature map, this one look at this area of input image and try to find the horizontal line. Okay, that's how it works. So I said suppose this feature map, goal of this feature map is about finding, let's say, horizontal line. Okay, then each node here in this feature map, actually this node look at this part of image and try to find horizontal line. And let's say this node here looks at this part of image and try to find horizontal line. Okay, that's what each node is doing in this feature map. Okay, that's the basic structure of feature map, and that's the goal of each node in feature maps. Okay. So this slide actually shows the example of sparse connectivity and weight sharing in feature map. The left-hand side here is an example of fully connected. This is the way we connect node in traditional neural net. So for example, suppose this is a hidden node, and this may be another hidden node or output node. Then as you can see, each node here is fully connected to the node in the next layer, right? This one is connected to every node here. In a similar way, each node here in this layer is also connected to every node in this previous layer. For example, this one is connected to every node in a previous layer, right? And this one is also connected to every node in this layer. So this is the way we connect node between layers in the traditional neural net, and this is called fully connected. Okay. And the way we connect node in CNN is different. As I explained earlier, in CNN feature map, we suppose this is input image, and this is one single feature map. Okay, then one node in this feature map is connected to a small portion of input. If you compare this with this one here is connected to every input here, right? But here in this feature map node, this is connected to only a small portion of input, in this case 3, right? And in a similar way, this node is also connected to a small portion of input, like this, right? And again, same thing, this last node is connected to a small portion of input image. Okay. So this is called sparse connectivity. This is the opposite of fully connected. So in fully connected, every node is connected to every node in other layer. In sparse connectivity, this node is connected to a small portion of another layer. Okay. In this case, input image. That's sparse connectivity. Another property of node in feature map is weight sharing. So this one uses a sparse connectivity. And another interesting property is for each node in the same feature map, this is one feature map, and these are the node in a single feature map. So each node in a single feature map actually shares the same weight value. Each node here has its own weight, right? So in this case, I say you have red weight, blue weight, and green weight, okay? And these weight values, whatever they are, these weight values are exactly same as these weight values, and also same all the way to the end, and all these weight values are same. Okay, across all these node in the same feature map. Okay, so that's why I colored the same. I colored the same color: blue, red, blue, and green. So this is called weight sharing. So there are two differences between the way we connect a node in traditional neural net and CNN. The first one is sparse connectivity. So each node here, each node in feature map is connected to a small portion of another layer, in this case image, okay? And second property is for each node, its weight values, okay, or sometimes called filter or kernel, and these weight values are identical across a different node in the same feature map. Okay, that's called weight sharing. We have seen the structure of convolution layer and the structure of feature maps and how these are connected and how these weights are shared. So this is kind of summary of what I explained in the previous slide. So in convolution layer, we have many feature maps, okay, and each feature map actually has its own purpose, okay. So for example, you have a certain feature map in a convolution layer. Maybe that feature map is goal of the feature map is to find an edge in an image. Maybe find an edge in the image, or as I said, maybe in a higher level, it can be something like the nose of human face, or ear of human face, etc. Okay, so as you in a higher level, the pattern you want to find using feature map is more higher level image. Okay, in lower level, the feature map finds some lower level images, lower level patterns like line, edges, etc. But in higher level convolution layer, we find something more more concrete, more realistic patterns like ear, nose, eyes, etc. Okay. So again, each feature map is trying to find a certain patterns in the data. So to do that, they use the technique of weight sharing and the sparse connectivity. So okay, each node in the same feature map look at different part of image, okay, and try to find pattern in that area, okay. And another node in the same feature map looks at another area of input image and try to find the same pattern. Okay, that's how the feature map works. So in general, we try to find many patterns in the image. So that's why we need more than one feature map. We need multiple feature map, and each feature map is trying to find different patterns. So because of this weight sharing and this sparse connectivity, the CNN network is well adapted to the translation or invariance of images. In the beginning of this chapter, we have seen the problems of the images in traditional neural net, right? We give a little twist of image, then we have a lot of difference in input data, okay? But in CNN, because of this weight sharing and sparse connectivity, this problem is easily solved, okay? So another advantage of CNN network is because of weight sharing and the sparse connectivity, actually it can reduce the number of parameters significantly, actually drastically. You can reduce the number of parameters in CNN, okay? So that's huge advantage because the number of parameters in CNN is drastically smaller than number of parameters in traditional neural net. It is not likely this one suffers from overfitting, okay? So that's a big advantage of CNN. Also, in CNN, each feature map finds a pattern out of data using feature map. So as we go up in the layer, in higher level layer, this pattern becomes more and more realistic. Okay, so lower level feature map, it finds line or edges, something like that. Okay, but in higher level feature map, we find something more realistic, like ear, nose, mouth, etc. Okay, so that's big advantage too. This slide shows some examples of feature map. So in this case, we have original image here, okay, and these are the filter values, the weight values, okay, and by applying this filter across these images, we have these images, convolved images, okay. So you apply this filter, image becomes like this, etc. Okay, so this is called identity filter. This is called edge detection filter. This filter is called sharpen, and etc. Okay, but one thing you have to notice here is we do not actually in many cases, in almost every cases, we do not provide these filter values. Okay, filter values are learned from data. Okay, algorithm decide these values from learning. Okay, you don't give values of filter by hand. Okay, this is going to be result of learning. Okay, that's the feature values. But in this case, it just shows the example of filter. Okay, the effect of filter. So that way you know, to just try to show the effect of filter values. Okay, this is another example. So if, let's say, this is the filter, again, this is not given by hand, this is learned by algorithm. So suppose this is the filter, okay, and this is result is shown here. This one is the filter, and this is output of feature map. This is filter, and this is output of feature map. Okay, so this one, these are the example of feature map using filters.
So we have seen the convolution layer, and now we're going to see another layer called pooling layer in CNN. So if you recall, one of the advantages of using convolution layer is that we can drastically reduce the number of parameters in the network by using the technique called weight sharing and sparse connectivity. So if you use a convolution network, you reduce the number of parameters drastically. The goal of pooling layer is actually you're gonna reduce the number of parameters even more. That is the goal of pooling layer. So actually what this pooling layer does is it comes right after convolution layer, and it actually reads the output of convolution layer as an input, okay, and then reduce number of parameters there even further. Okay, that's what this pooling layer does. So in many cases, this pooling layer comes right after a convolution layer, but actually in many cases, you know, this pooling layer, multiple pooling layers can come in sequence. So as a matter of fact, you can arrange between this convolution layer and pooling layer in any arbitrary order. It's up to you actually. So anyway, the goal of pooling layer is, again, as I said, reducing the number of parameters even further in the network. So the detail of pooling layer will be explained. Next slide.
This slide shows how pooling layer works. So for example, let's say we have a feature map. Okay, this is the feature map. And right after this feature map, suppose we have a pooling layer. And the way this works is as follows. So again, this one in pooling layer, we have in this case 4 nodes, and this node look at this part of feature map, and this node in pooling layer looks at this part of feature map, and this one look at this part, and this one looks at this part. Okay, and the pooling layer is basically summary of feature map. So you're gonna summarize this feature map in pooling layer with reduced dimension. So original dimension is 4x4. In pooling layer, it's 2x2. Okay, so you're gonna reduce the size of feature map into a lower dimension. That's the goal of using pooling layer. So this one look at this part, this one look at this part, and this one look at this part, this one look at this part. So basically, this is summary of this area. This is summary of this area. This summary of this area. This summary of this area. Okay. Then question is, how do you summarize? What do you mean by summary? Okay. So there are two methods actually more than two, but these two are very popular. The first method is called max pooling. So max pooling is, I said this is summary of this area, right? When you summarize this, basically in max pooling, this one takes the maximum value of this area. Okay, so this one, take a look at this part and choose maximum value. In this case, 100. So 100 comes here. So this one choose maximum value of this area. Okay. Again, same thing here. Max pooling here in this case is this one choose maximum value in this area, which is 184, right? This one choose maximum value here, which is 12, and this one choose maximum value in this area, which is 45, right? So that's how it works in pooling area using max pooling. Another pooling method is average. So in this case, when you summarize, you calculate average of data. So in this case, this one, look at this and calculate average of this, which is 36. This one, look at this part and calculate average of this, which is 80, etc. Okay. So anyway, pooling layer is about reducing the dimension of feature map. Okay. So in this case, original feature map is 4x4. Now in pooling layer, you're gonna reduce it 2x2, right? So when you summarize, you can use either max pooling or average pooling. We have some other pooling like summation pooling, etc. Okay, but this max pooling is the most popular pooling method we use in CNN. Okay. So one common procedure for pooling layer is max pooling. Okay, so max pooling, you simply look at the area and choose the maximum value. Okay, that's max pooling. Okay. The idea of pooling layer is as follows. Okay, what is the purpose of using pooling layer? Okay, so the first reason of using pooling layer is, again, as I said, you're gonna reduce the dimension of feature map. You're gonna reduce the parameter even for number of parameter even further. Okay, by reducing the dimension of feature map. Second reason of pooling layer is, so this one choose maximum value of feature map here. Okay, so do you remember in each node, each feature map has a purpose in it. Okay, let's say this feature map is about finding horizontal line. Okay, and each value node here is value of node here tells us that, well, in this particular area, I found horizontal line or not. That's what this value means. Okay. So, for example, the value is 184. And suppose this feature map is about finding horizontal line, okay? Then this node has very high output. That probably means this node is saying, I found horizontal line in this area. okay, this node looks at a small area of image, right? So in this, it's like saying, this node is saying, I found a horizontal line in this area, okay? This 0 means this node look at another area of input, right? And this 0 means, well, I look at this area and there is no horizontal line, okay? You can interpret this as follows, okay? So in pooling layer, what it means is, now this look at these 4 area, okay, and look at these 4 area, and if you choose maximum, right? So if there is any horizontal line in this 4 area, then this maximum value comes in and say, it's like saying, okay, I found a horizontal line in this area, in more wider area. I found horizontal line in this area, okay? That's kind of interpretation, the meaning of this pooling layer, okay? So pooling layer, so the node in pooling layer looks at a certain area of feature map and choose maximum value of the area, okay? And that becomes the value of pooling layer node, right? So if you remember the meaning of feature map value, so in each node of feature map, okay, its value means, so it's suppose each one node in a feature map value is very high, its output is very high, okay? It is like saying, this node is saying, telling us that I found a horizontal line. Suppose this feature map is about finding horizontal line. So this node is saying to us that I found horizontal line in this particular area, okay? So if node value is high, that means there is a horizontal line in this area. And there is another node in the same feature map. Let's say its output is very low, like 0. Then it is like saying there is no horizontal line in that particular area, okay? That's the meaning of feature map values. So in pooling layer, each node in pooling layer, look at a small area of now feature map and choose maximum value, okay? Then think about it. The meaning of the value in pooling layer is basically, so each one node in pooling layer look at a small portion of feature map and choose maximum, right? So that means each node in pooling layer now look at the more wider, more broader area of input data and tells us whether there is horizontal line there or not. Okay, let me repeat. Each feature map value, okay, each node in feature map tells us whether there is horizontal line in that particular area, right? Pooling layer node look at a small area of feature map and choose maximum value, right? So that basically means now each node in pooling layer now look at more wider area of original data and tell us whether there is horizontal line there or not. Okay, that's the meaning of the value in pooling layer node. Okay, so that's the pooling layer node, and but one of the problem of pooling layer is so yeah, in pooling layer, it, as I said, it tells us whether there is a, let's say a horizontal line in a certain wider area, whether there is horizontal line or not. Okay, in a higher level, it tells us, it tells us whether there is a nose, a human nose in human face, there is nose in this particular area or not. It tells us, okay. And also in other feature map, it can in other pooling layer from different feature map, it tells us whether there is eye in this particular area of image, etc. Okay, so it tells us. So in a higher level, let's say there is each pooling layer tells us where there is ear in this image, and there is a eye in this area, etc. Okay, so it's good, but the problem of pooling layer is it tells us whether a certain feature, certain pattern exists in the image. Okay, it tells us whether it exists or not. Okay, whether this image contains this human face, whether this image contains, let's say, eyes or mouth or nose, etc. It tells us whether that pattern exists in the image. Okay, but problem of this pooling layer is it does not tell us where. Okay, suppose in pooling layer, if pooling layer tells us that there is nose here, and also the other pooling layer says there is mouth here, and there are some two eyes here in the image, then yeah, it's good, right? We have human face, two eyes, one nose, and one mouth. That looks good. But what is missing here is their relative positions. Okay, pooling layer tells us we do have one mouth, one nose, two eyes. That's good, right? But it doesn't tell us where these patterns are. Okay, so for example, let's say in your image, the mouth is above your eyes, etc. Okay, then it is not human face, right? But in pooling layer, it doesn't recognize. It does recognize the existence of patterns, but it does not recognize their relative positions. Whether these eyes are below a mouth or whatever. Okay, so it doesn't recognize relative positions. Okay, so that's the problem of pooling layer. So because of all these problems, sometimes in these days, some people do not use pooling layer at all in CNN. So in these days, you can see many CNN network which consist of convolution layer only. Okay, no pooling layer. Actually, the Jeffrey Hinton, the inventor of actually deep learning, actually he didn't like this pooling layer. Okay, and he actually come up with another improved method called the capsule network instead of pooling layer. So we will see. Okay, so anyway, pooling layer is very good idea, but it has some problems, and because of problems, you can see many CNN networks which consist of convolution layer only, no pooling layer. Okay. But it's still pretty good, okay? So that's the pooling layer. So we have seen the structure of convolution layer and pooling layer. So when you construct a CNN network, you can use any sequence of convolution layer and pooling layer. You can go like convolution layer, plus pooling layer, plus another convolution layer. So you can use any combination of convolution layer on the pooling layer. Okay. But one thing you have to remember is the final layer of CNN should be fully connected layer, just like the layer in traditional neural net. The final layer must be fully connected one. Okay, there is no weight sharing or sparse connectivity in the final layer of CNN. Final layer is always fully connected layer, just like traditional neural net. Okay, so that's basically the structure of CNN. You can put as many convolution layer or as many convolution layer as you want in CNN. But at the end, you put a fully connected layer at the end, okay, for output. So that's structure of CNN. And when you train it, basically you use the stochastic gradient descent and the backpropagation, just like you train traditional neural net. You use backpropagation, stochastic gradient descent, okay. But when you use backpropagation, you need a little bit of modification, because in CNN we use weight sharing and sparse connectivity. So we did a little bit of modified version of backpropagation in CNN. Okay, then you train this CNN using this modified backpropagation. Then what happened is, to remember all these the weight values, kernel values. Okay, all these weight values are automatically determined to detect important patterns in the image. Okay, that's the beauty of a CNN network. So this picture shows an example of a CNN network. We have input, okay, and we have one convolution layer. So as I said, this convolution layer has many feature maps, right? And as I said, again, this node is connected to a small portion of original data, okay? And these weight values are called convolution filter or kernel. So after this convolution layer, we have pooling layer. As you can see, the dimension is reduced. Okay, so original dimension is 28. Its dimension is now 14 by 14. Okay, we use max pooling for pooling layer. So after pooling layer, we have another convolution layer. Okay, and we add another pooling layer here. So you can choose whatever combination you like. You can add another convolution layer here, or you can add another pooling layer here. Okay, so you can choose whatever combination of convolution layer and pooling layer you want. Okay, but one thing you have to know is you cannot use pooling layer only. Okay, it fails. So you should have at least one convolution layer in your CNN. If your network consists of a pooling layer, it fails. It doesn't recognize. Okay. And at the end here, we just flatten this. Flatten means you convert everything here into one dimension data. It's flattened here, and this is now becomes fully connected. So we have two layers of fully connected, because this data is too big. We have two layers of fully connected layer here. Okay, and the entire network is trained by using backpropagation. Okay. So what happened is all this data, all these weight values, kernel, these weight values are automatically determined. Okay, automatically determined to extract features, extract some important pattern or features in this feature map. Okay, so that's how it works. So this is the example of applying CNN to car images. This is the value of lower level feature map, and this is the value of middle level feature map, and this is the value of higher level feature maps. As you can see, in a lower level feature map, the image, the pattern we're gonna find is a little lower level, very primitive patterns, the line or circle, etc. Okay, so as you go to higher level, the pattern we are looking for is more realistic, more abstract, right? So that's how this CNN network finds patterns automatically.